Hey AP Chemistry. This quick video is going to go along with photoelectron spectroscopy POGL. It's a pretty important concept because this is an AP Chemistry course. Somebody on the AP test writing committee loves this topic. So we're going to take a look at it. But what I like is that it's very unique graphing. And the graph will give you some really important information. So we're going to take a quick look at this. So what is photoelectron spectroscopy? Well, it's a process that allows scientists to determine the ionization energy of valence electrons for all of the electrons in an atom. So basically what they do is they take a sample of atoms that have a known energy, and the photons kick out the electrons, and then the scientists measure their kinetic energy. So the energy from the photon, the light particle, is used to remove the electron. There's your ionization energy. And then the excess energy becomes velocity or kinetic energy for the electrons. And so you wind up with this lovely little equation that the kinetic energy of the light particle must equal the ionization energy plus the kinetic energy of the electron. If you think about it, if I'm an electron and I'm just sitting here minding my own business and all of a sudden this light particle comes in, bam, smashes me enough that it knocks me out of orbit and I keep moving. That's what we're talking about here. So the light particle has enough energy that it can hit me, the electron, knock me out of orbit, and I keep moving. Now, if the ionization energy is the only thing that's met, I get knocked out of orbit, but then I don't move. If you are interested, you can look up Khan Academy. There's a pretty good video that kind of goes over this as well. Since ionization energy is a key component to photoelectron spectroscopy, let's just take a quick review and remember from last year what this means. Ionization energy is the energy it takes to remove an electron. And think about what it takes to remove an electron. Electrons are held by the nucleus, and that depends on several things. Distance is one of the main keys. Now remember Coulomb's law. Positive negatives attract, like charges repel, and distance affects them. So if an electron is far from the nucleus, it's a lot easier to remove. If it's really close to the nucleus, it's going to be more difficult to remove. So when you're thinking about ionization energy, you want to consider how big the atom is, how positive the nucleus is, how far away the electrons are. All of that will play into how difficult it will be to remove an electron. The more difficult, the higher the ionization energy. Now, light intensity, simply the number of photons that strike a surface, has nothing to do with it. It has to do with the amount of energy. It must be greater than the work function to emit an electron. And if you take physics, we do a really great simulation on photoelectron spectroscopy and demonstrate that light intensity doesn't make a difference. In this POGL, and probably on the AP Chemistry test, you're going to see a graph that looks like this. So the first thing I want you to always notice about a graph is what's on the axes. Well, on the y-axis, if you turn your head a little bit, it's the relative number of electrons. And then on the x-axis, you have binding energy. Now, the first thing you should notice is that the x-axis seems to be backwards. We start with 1,000 and we end at 0, and that's really, really key. It's binding energy. It's how much those electrons are held to the nucleus. So where the y-axis meets the x-axis, there's your nucleus. So don't you expect the electrons closer to the nucleus to be held more tightly? Yeah. So the very first peak that you see, the one that's just to the left of the 100, those are the electrons closest to the nucleus. And then as you move to the right, those are farther and farther from the nucleus. Each peak represents one of the subshells, one of the little orbitals, like 1s or 2s or 2p. So if you look at that very first peak, the one by the 100, that's your 1s. Well, how many electrons are in the 1s? 2. So go to the next peak. Did you notice that it's the same size? Guess what? That next peak is 2s. 2s has 2 electrons. Now you have to kind of play a little bit of one of those games like this, but if you look at the next peak, that really big one, isn't it 3 times the size of the one next to it? That's because it holds 6 electrons. There's your 2p. Go to the next one, the one that's right about above the 1. 3s. It holds 2 electrons. Now that next one is obviously half the size, so 1 electron. Oh, 3p, 1 electron. So you might have figured out what I was doing on the last slide. That's right. You can look at this graph and determine what element it is. Well, we know we have 1s2, 2s2, 2p6, 3s2, 3p1. Who resides in the 3p1 box? That's right. It's aluminum. And if you don't believe me, you can count the electrons. You have 2 plus 2, which is 4, plus 6, which is 10, plus 3, which is 13. Just in case you don't believe me, confirmation, it's aluminum. But I want you to recall that as you go across a row on the periodic table, the ionization energy is going to increase. Why? The atoms are getting smaller, the nucleus is becoming more positive, the electrons do not want to be given up. They would much rather steal electrons. Thus, the starting binding energy for F is going to be much, much, much higher for carbon. The last little part of this POGL involves the equations, which you probably have already seen on other PowerPoints and even on the homework assignment. A couple of equations. One is E equals HV, and that's energy equals Planck's constant times frequency, not velocity, frequency. And then C equals lambda V, and C is the speed of light, lambda is the wavelength, and then V again is frequency. And you can combine these two. Go ahead and do the algebra on your own if you'd like, and you get the combined equation. Just recall the units, because you have to be in certain units or this does not work. Energy is going to be in joules. Planck's constant is joules times seconds. Frequency is either hertz or second to the negative 1. I recommend using the second to the negative 1 or 1 over s, because that's going to help you get those seconds to cross off. Speed of light, meters per second, and the wavelength has to be in meters. Well, typically our wavelength is given in nanometers, so probably the first thing you need to do is convert nanometers to meters. And remember that 1 meter is 1 times 10 to the 9th nanometers. And again, you're probably going to have to use these equations either together or the combined equation. So sometimes you don't know the frequency. So you use the E equation to find frequency, and then you can find wavelength, or flip it around. So just get used to having to use these equations in combination. Now go work on the POGL and let's see if all this will make even more sense to you. They use a great analogy about kicking a soccer ball out of a ditch that should help you solidify what's happening with photons and electrons in photoelectron spectroscopy.